Is started. We're recording. Yep, we're good.
Okay, well, thank you everybody for joining us today. And our webinar today, we're going to cover printer supports, stencils, and squeegees. We have a lot of information to cover, so we're going to dive right into printer support tooling. So the kind of things we are going to talk about is why is support critical, and what you may see if you don't have enough support in your screen printer, and what are the different options for support. And we're going to talk a little bit out there, pluses and minuses and their limitations and how they compare to each other. So you can make an informed decision on which way you want to go with your support. So first of all, why is it critical? In the print process, it's critical that the PCB is firmly held against the stencil throughout the print cycle. This helps with gasketing. And what gasketing is the seal between the PCB and the stencil. Because the print head exerts a lot of pressure, and that could flex the PCB and the stencil during the print. And if you don't have enough support, it will compromise that gasketing. And that will allow paste to bleed out under the stencil, as well as cause other defects such as excessive solder, wet bridging, smear or solder balls on your mask. It can also create insufficiency because the paste may not release from the stencil properly, and it can also misalign prints. There is an easy way to check for gasketing. It's during the setup of the printer. We call it the tap test. So what you do is you bring the board to the stencil height and simply tap or push on the stencil in multiple locations and look for movement. If there's any gaps between your board and the stencil, you'll see it by doing that. So here's a video of showing what a bad gasket looks like and what a good gasket looks like using the tap test. So this is a bad gasket. You can see movement between the stencil and the pads on the board. So that indicates there's a gap. You're not going to get gasketing there. When you do have proper support, it's going to be nice and tight between the stencil and the board, and it needs to be tight to be right. Make sure we test for our gasketing. There are 4 main types of supports: magnetic pins, compliant pins and support, machine plates, and process carriers. Each one has its pluses and minuses to consider, so you can select the right support option for your process. The first one is magnetic pins. Now, magnetic pins usually come with the machine when you buy one, and they're very simple in design. They come in various shapes, sizes, from pins to plates and things of that nature. Pins can be set up for different assembly layouts. So if you have a single side assembly, the pins can be packed real close together to get optimum support. And being that they are simple in constructions, they are very low maintenance. You just have to keep them clean. The minuses, when we talk about magnetic pins, placement of these pins are very highly operator dependent. When you have double-sided boards, which means there's parts on both sides, it's critical to place these away from parts or damage will occur. And oftentimes this damage could go undetected since it's already been on an inspected pass. To prevent this, you can use plexiglass templates or mapping to use to locate the pins. And those things have to be stored and be able to be easily accessible for your setups. Some machines have options to machine place the pins, which it uses the camera gantry to pick and place the supports. That does remove the human placement aspect, but it can be an expensive option for your printer. Some other printers may have a laser pointer on the camera and things of that nature to help guide the operator to place it correctly. Now, it can be difficult or nearly impossible to get needed support in critical support areas of highly populated boards. And the setup time that it takes to place these manually is significant, and that's going to increase your changeover times. Compliant pin supports, these have pins or surfaces that form to the topography of the PCB, including any parts that have been populated first pass during a second pass setup. Pluses for this type of support: the contact areas have soft silicone rubber tips, and that will prevent damage to any parts that they touch. They can be used with most assembly layouts, making them very flexible. And they support, their pin style support, the pins are less than an inch between the pin and pin spacing. So it provides a significant support contact area to your boards. The changeover using these supports can be very quick. You simply just add or remove bars to fill in the work nest area for your particular assembly. Some of the cons or the minuses when you're using this pin style: you have to trigger the pins. If you trigger the pins with each print, it does require some integration with an I/O on your machine, or you have to install an external sensor. With the sensor placement, depending on the machine, it may change the timing when the pins fire, and they may fire before the board touches the stencil. And when you have a thin board, it could contribute to some board bow. They also require frequent cleaning PMs, because as debris or solder paste build up on the pins, it may prevent them from firing. And I know they've made some improvements over the years, but they still require cleaning time to time to keep the pins firing properly. One of the other issues with this type of support is that the soft silicone rubber tips on the ends of the pins can fall off. Without the tip on there, you may not contact the PCB at all, or you could have a hard pin against a delicate part, causing damage. It also, even though these pin to pin spacings are less than an inch, it can be difficult to get good supports in all areas, especially when you have heavily routed boards or parts near railing, critical parts near the rails. You can stagger the support bars, and that helps spread out the support so they're not all in a straight line across the width of the board. And that helps also even out the support across your board. Next style is dedicated machine plate supports. These plates are machined usually out of aluminum, and they are securely mounted inside the work nest of the machine. It's a very stable and consistent support. You can also get support into much smaller areas since it is machined, so you can get closer to parts, which will allow you to achieve better support on heavily populated boards. They can also utilize a vacuum option if you have that option in the machine, and what that will do is pull down the board against the support fixture, and it'll hold it much flatter in case you have a little bit of bow. The minuses, if you decide to go this way with a dedicated plate, is that it is assembly specific, and therefore it really needs a stable product design. You don't want to have a design that's going to change, because that make this plate incompatible, and it could be very expensive to keep replacing them. Because they are expensive, because you have to consider the design and the machining NRE costs, and you're only usually getting one or two for an assembly, and the lead times may not be very good when you're considering NPI runs. But again, they work very well for stable product. Storage of these plates can also be a concern because they can be rather large and heavy for larger assemblies. So they may be very awkward and take up a lot of space. Now, even though a lot of these plates are made out of aluminum, with the advancement of 3D printing, these supports may be made out of a much thinner and lighter weight material, which would help improve that storage and handling aspect of them, because thinner support fixtures require less space. And these thinner support fixtures could then be mounted over a secured block or base that's in the machine, and that will also help reduce the changeover time that it takes to unbolt these supports out and replace it with another one. The last type of support are process carriers. These are sometimes a necessary evil. The pluses of using process carriers, and we're talking about the ones that run from print all the way through reflow. They do provide good support, and you can get support similar to a plate. They're primarily used for flex circuits or odd shaped boards where you don't have straight edges or rails to run them down the assembly line. Or maybe you get a batch of one-up boards that are not in a panel and you want to be able to, run them more efficiently down your line. The minuses of using process carriers, especially the ones that run from print through reflow, they do require a high temperature stable material since they are going through the oven, and they do require cooling back to room temperature before you can reuse them. Because if a hot pallet is reused at the printer, that heat will transfer into the assembly, into the PCB, and the paste could start to slump or have premature flux exhaustion, and you won't solder properly. So what you need to have is some sort of cooling station to quickly draw the heat out. And some people will say, oh, I'll get a box fan from Walmart. That'll blow a lot of air. It makes for a cheap cooling station. But keep in mind, those types of fans are not ESD safe. You also have to supply the line with enough pallets so you don't go down for that terrible waiting on pallets downtime. And depending on the cycle time of your product, your cool down time of the pallets, the line length, how many stations you have in your line, and the production requirements, the number of the pallets that you need may be significant, over 30, and that will drive up the costs overall. Plus, when you have a large quantity of pallets, it also requires significant storage space to store those when not in use. Now, they will have wear and tear from the heat cycling and also general handling, so you are going to need to repair or replace these from time to time. And since there's no positive board clamps or hold downs allowed to be above the top surface of the pallet because of the print process, you have flush pins or spring pullers or pushers are often used to secure the board in the pallet. And this can be difficult to hold thin or warped boards. Some people will say, well, I'm going to use an ESD capped on tape for a quick go-to board securing method. But that's not a cheap option either. And if you try to use other type tapes, cheaper tapes, they may leave residues, and they can also be an ESD source. Now, there is a material out there. It's called TaxSeal. It's by a company called CeTaQ, and it is a reusable carrier tape. It can be applied to the bottom of the pallet, and when you put the board onto it, that material has some tackiness to it, and it'll hold the board in place. It does hold up fairly well. I've used it many times, and it doesn't leave any residues on the board, but you will start to lose that tackiness because it's going to collect dust and flux residues and things like that. But they do have a method to restore that tackiness. Also, flux buildup through your oven is likely to occur on the pallets over time in use. So you will have to clean these to prevent contamination buildup on your pallets and transferring that to your boards. So keep in mind, we covered the main 4 types of support. No support option is going to be 100% solution. Everything has its drawbacks, and they might not be applicable in all cases. But regardless of the type of support you use, you need to inspect it before its use and make sure that you keep those supports clean, because solder drips from the blades could get onto contact surfaces, and they could transfer to a pad on the bottom. And then when you flip that board over for second pass, that solder may have balled up in the oven, creating a huge solder ball on your board, and you will damage the second pass stencil, which will take down your whole line. Always keep in mind, more support makes for a better print. But make sure you're not causing any damage to the first pass parts. And keep in mind, if you are involving a person in doing the actual setup, this always creates opportunity for variation and error. So try to minimize how much that operator or technician has to engage with that setup. You want it to be quick, simple, and repeatable. And also, you want to check your support setup before you hit the go button. To do so, you're going to want to load the board and raise it so that the supports are touching the board. And you don't want to have a stencil in at this time, because you want to check it for flatness. You want to check it for soft spots or possible part interferences. Once you determine that, yes, the pins or whatever is in the right places and you have good support, then you're going to want to go back, load that stencil, load the board to stencil height, and then do that tap test to make sure you have gasketing. So that was a quick overview of supports. Does anybody have any questions in the chat?
I don't see any questions in the chat, but I will let everyone send messages.
Okay, excellent. Well, we're going to move on to talking about the stencils themselves and how they contribute and are critical to quality. First thing what we want to talk about is the anatomy of the stencil, how the stencils are constructed and how that plays a part in its overall performance. And then we're also going to talk about some design tips for success, so you can make some adjustments to get optimum performance and quality out of your stencil. So most stencils consist of 5 key components. Each perform a purpose and will impact the results. The first one is the frame, and there are frameless stencils out there that we'll get into in a little bit. But regardless if they're a framed stencil or frameless, they still will get mounted in a type of frame. And this gives you the rigidity to the stencil. It also offers some protection from damage on the edges. Next is the mesh. The mesh is made out of various materials, and they can be held at different tensions. In the case of frameless stencils, the foil is mounted directly to the usable frame, so there is no mesh in one of those reusable frameless stencils. The epoxy bond, or the weld between the foil and the mesh and the frame, this is what gives the foil its rigidity. And also, I'd like to point out that with the frameless stencils, there will be no mesh or epoxy bond. Then we get to the foil itself, and this is what contains the artwork. And this also determines your height of your paste deposits, which correlate to volume. And then you have the artwork itself. This is the design of the board and the apertures that defines the shape and the sizes of all your apertures that match up to your pads. Now, of course, you want to get a stencil frame that is big enough to fit in your printer, or have mounting holes in that frame so you can attach an adapter. The frames are usually made out of a welded aluminum tube or even a cast aluminum. Now, with adjustable stencil frames, you can, in your screen printers, that can give you some flexibility as far as using different size stencils in your printer, maybe from 29 to 23, or you might use smaller stencils and attach a frame adapter to fit onto a larger stencil shelf in your screen printer. But keep in mind when you're using these frame adapters, it is super critical that the stencil has threaded mounting holes so you can actually mount the frame adapter. But it also has to sit flat to the frame, because if it doesn't sit flat, it's not going to sit flat to the board, and it's potentially going to cause you gasketing issues. And you can, from time to time, you might get a warped tube frame. It's pretty rare, but it happens, and that'll also affect your gasketing. Now, using the standard thicker frames, which are about 1.5 inches, I believe, those do require a fair amount of storage space. And there is some low profile, or what they call space saver stencils. And those can allow 2 stencils to fit in the same space on your stencil rack as a standard thickness frame. In any case, whatever stencil you use, proper storage is critical to protect the stencil from damage when they're not in use. You do not want to lay it flat on tables or in any way that the foil can come in contact with anything, because that can easily cause dings and damage your stencil. And you don't want to store stencils in places where they can easily fall over or get kicked, like on the floor or leaning against things. You're going to want to have them in a dedicated rack system or some other way to protect them and store them. Now, moving on to the mesh. The mesh is what connects the frame to the foil, like we mentioned, and that uses either glues or a type of plastic welding to secure the mesh to the foil. And the tension that the mesh holds the stencil at will impact the snap off as you raise the stencil off the board. It can also affect your gasketing and can also affect your alignment. So any cuts or separations of the bond between the stencil and the mesh will reduce the tension and impact its performance. So if you have cuts or separation in the mesh, it's better just to replace it than try to repair it, because you won't be able to retain that tension. Handling and cleaning, those are the 2 biggest causes for mesh bond breakdown or damage, because you can have wash chemicals, excessive heat, or possibly leaving too long in an ultrasonic bath. That will break down the glue bonds and your foil may pop out of your stencil. For high tension stencils, the mesh is made out of a stainless steel, and basically higher tension stencils make the stencil foil more rigid, so it can help with snap off release and performance on finer pitch parts and miniaturizations. Now, we mentioned frameless stencils. With a frameless stencils, it does away with the fixed frame and the mesh of the traditional stencil. They have a reusable frame, and they use pneumatics to clamp and secure the foil and create that tension to the stencil foil in the frame. And of course, having no fixed frame reduces storage space needs significantly, but the unmounted stencil foils need to be very carefully handled to prevent any damage, because they lack the rigidity and the protection provided by a traditional frame. Now, I haven't personally used frameless stencils, and I know there's plenty of opinions out there on them. So if you're thinking about going with a frameless stencil, make sure you do a proper validation to see if it's a good fit for you. The foil itself. Now, the foil selection of the foil thickness and the base material that you make the foil out of is a critical aspect of the design process, because the thickness of the material impacts the volume of the deposit, and the material itself will impact the release out of the stencil. Common materials are various types of stainless steel alloys, such as stainless 304 or 316, a type called PHD, or fine grain stainless steel, as well as nickel can be used for stencils. Now, what differentiates these materials is these different materials have different internal grain structures, which impacts how smooth the aperture walls are after you cut it with a laser. And the smaller the grain structure, the smoother the wall. The smoother the wall, the better the paste release. So I've got some images here that show you different grain structures for different materials. They're all cut with the same laser and inspected under SEM, so you can see what the different grain structures are. The complexity and the technology on the board, how small or fine pitched, that all needs to be considered when you're selecting that foil material. Because of the different grain structures, the transfer efficiencies will differ. And they have different thickness tolerances, and also they cost different relatively. So a higher grade material will likely increase the cost of your stencil as compared to a standard one. So you need to carefully consider the technology on the board when you're selecting the material. So complexity, go with a higher grain, finer grain stainless if it's a high complexity board. Now, I mentioned transfer efficiency, and what that is, it's a way to measure or express how well the paste releases out of the stencil. It's a comparison of the paste left on the pad after print versus the paste left in the apertures of the stencil after the stencil releases from the PCB. So if you have a high paste transfer efficiency, it means that nearly all the paste deposited actually stayed on the pad and doesn't really stick in the stencil. That's what we want. Your paste deposits will look crisp, and you'll have the desired volume that you designed in. Now, as transfer efficiencies drop, meaning more and more paste is being left in the stencil aperture, the paste deposits will start to appear having poor print definition, poor shape. You may get some dog ears, and also result in lower volumes, which could cause potential defects after reflow. And when you look at these different materials, the difference in transfer efficiency between these materials, it can be high as 10 to 15%. So it is a significant contributor. Now, granted, there are other factors that contribute to the transfer of paste to your board, but again, stencil material is a big contributor. So one of the biggest advances in stencil technology over the years has been the introduction of advanced nano coatings. What these are very thin layers of material that's applied to the stencil and bonds to it on a molecular level. The thickness of these nano coatings is between 1 and 10 microns, which means it has negligible impact on the aperture size. So you don't have to worry about making adjustments to enlarge apertures for coatings. Now, what the purpose of the nano coatings are is to provide a smooth hygroscopic surface, which means they repel liquid. In this case, it's the flux in the paste that it's going to repel. And it's going to repel that flux from the stencil. Since it repels the flux, which is tacky, the paste wants to stay together. Therefore, it's going to stay on the pad, and that's what improves your transfer efficiency. Now, there are two types of coatings. One is a wipe-on, and one is a cured-on coating. The cured-on coatings penetrate the apertures of the stencils, coating the entire aperture wall, so it has a much more significant impact on printing than the wipe-on. It also has a longer lifespan than the wipe-on nano coatings. Now, I've got two images shown here, and this is from a study done by Blue Ring and Greg Smith, where he compared an uncoated stencil to a nano-coated stencil. So you could tell it's making for a very smooth wall that's compared to uncoated. And this is what's going to improve your paste release, because it removes the effect of the grain structure of the stencil material. Now, both types of these nano coatings, whether it's wipe-on or cure-on, they can also reduce the need for stencil cleaning between your prints, which of course can translate into saving money on wiper paper and cleaning chemistries, as well as keeps your cycle time down. However, the cleaning materials, they need to be compatible with the coatings. So for example, if your roller paper is really coarse, it can actually start to rub off the coating off the bottom of the stencil. And chemicals can also break down and remove that coating over time. So make sure they are compatible. So this table shows the impact of material selection as well as the impact of nano coatings. This was a study conducted by Greg Smith of Blue Ring Stencils back in 2017. And what they did is they looked at the different stencil materials. They focused on a very small aperture with a and measured how well the paste released from that aperture from different foil materials. And then they took that same material and coated it with cured on nano coatings. And what the results shown is that you do get different transfer efficiencies between materials. And that is the TE uncoated versus the TE coated. And it also shows you the effects of the application of the nano coatings, and that is in the CV uncoated and the CV coated. Now it's all, oops, let me go back. Now it's also important not only to measure how much paste is released from your stencil, but it's also important that it is consistent paste release print after print. And this factor can be done by looking at the coefficient of variation, or CV. What CV is it's a calculation, and it's calculated by dividing the standard deviation of the volume measurements by the average of the volume measurements. And then you convert that into a percentage. And the goal is to have a low CV, less than 10%. Because if it's less than 10%, you have low variation. Low variation means you're going to get more consistent results and higher quality. So definitely in this table, you can see the consistency of release in the uncoated stencil materials, as well as the impact of nano coating, lowering that variation and the CV value. Now, what about cost impacts on the stencil? Well, you know, your frame style, your mesh tensioning and mesh material, your foil material, whether or not you're applying nano coatings, these can all contribute to the performance of the stencil, but it will also impact the cost of the stencil. So if the PCB design is not highly complex, which is it has no miniaturization, so no transfer efficiency or CV concerns, does it really justify the cost of adding all these improvements to the stencil? Probably not. You need to consider and weigh the bang for the buck in the investment in the stencil. Does it justify it? And that's for the process engineer to decide. Now we're going to talk a little bit about stencil design. Designing.
Ray, sorry,
oh, yes,
sorry for interrupting, Ray. Do we have time for some questions? Is this is this the break point?
What's it going to be? But it can be now.
Okay. From Miguel, can I get the name of the tacky material to be used to hold the PCB?
It's called TacSeal. It's spelled TACSIL. And the company is Taconic, which is spelled TACONIC, I believe. A lot of the stencil or the palette manufacturers, they're aware of this material and they use it. It's one of their options, at least here in the States.
All right. And we had another question from Szilard Balarka. We are using Space Saver datum in parentheses, meshed tension stencils. What is your opinion about frameless versus framed stencils? Is the first question.
Okay. Again, Let me answer the first question. I haven't personally used frameless stencils. I know a lot of people do, especially for maybe NPIs or things of that nature. There's a lot of opinions out there, you know, do they hold up the tension over a long period of time? The handling concerns of a foil that it does have a little picture frame around it to give it rigidity and protect the whoever's handling it from getting cut, but it's a much more flimsy material because there's no fixed frame. So you lose that. Now the frameless stencils do come in a high tension, and if you're using the datum mesh, that's a high tension stencil. So they do come in high tension. So, but I would suggest just do a little evaluation on your own. I'm sure you can do a demo and see if it works for you.
Okay, question 2, following that, is there any requirement / standard for tension measurement / monitoring?
Not that I'm 100% aware of. I know the stencil houses, they tension for a standard about 40 newtons. And then for a high tension, I think it's around 60 newtons. One way I looked at tension is, of course, you're going to see it in the print. If it's not good tension, it's the foil is going to bounce as it releases. You're not going to get good print results. But I would just, push down on the stencil. I think you can also get, some tooling, so you could press down and get make sure it achieves a certain rigidity or value to correlate to how much it's tensioned.
Okay. And the last question from Daniel Stanfill, that table showed PhD as slightly more expensive, while the fine grain appeared to perform better in every metric. Is that true?
Yes, and that those values were just is looking at the square inch value. I was actually surprised, and of course this was also a one of them AI searches, so take it with a grain of salt. I expect the PhD, when you buy those have almost became the standard for stencils, and they are cheaper in price, at least in my experience, cheaper in price than the fine grain.
Okay. All right. So that's what we've had for questions so far since the last break, and I apologize for taking you out of your your routine here. Let's get back to finish stencil design.
Okay, yep. So now we're going to talk about some stencil design tips. Like I mentioned, the artwork, or we call it stencil design, this is the most critical thing, and this will make or break your print process. Now, apertures for the stencil, they do need to be modified to reduce the opportunity for gasketing issues, as well as modifications in their size, shape, and thicknesses to achieve defect-free results. The following, the standard IPC-7525 is a good start for stencil designs, but that assumes that the designer followed good design criteria and followed IPC criteria for pad design. And we know not all designers follow the same set of design rules or just ignore them altogether. So you may find that you need to do custom adjustments past the IPC. And also IPC standards, they can't accommodate for all challenges, especially all this new technology that's coming out. And they also don't really know how your factory operates. So it's a good idea to develop a controlled internal set of design guidelines that you can share with your stencil vendors. Because if you have multiple vendors, good design standards help you get consistent results, regardless of where you get the stencil cut. And if you have inconsistent designs, this can pretty much guarantee you're going to have issues and adjustments will need to be made. So when you're modifying the stencil apertures, there are some key criteria that need to be met to help ensure that you're going to get good results out of your print. The first thing we already mentioned was gasketing. So we talked about it in terms of support and also stencil construction, but stencil aperture reductions, those are the key to the gasketing. And what gasketing does, it helps contain the solder paste to the pad. So if you have poor gasketing, that's going to allow the solder to seep out under the stencil and could cause various print issues and post-reflow issues, such as solder balls or bridges, things of that nature. And it also may cause you to clean your stencil more frequently because that solder is going to start building up on the bottom of your stencil, which is going to cost you a little bit more in consumables. So to accomplish this gasketing, typically the apertures are reduced by about 1 or 2 mils or so. So that helps ensure that when the stencil is aligned to the board, the aperture window is completely on the pad. And this helps ensure there's no pathways between the stencil and the pad to allow paste to squirt through. And also keep in mind, this is reductions done on the final pad size after the PCB fabrication. The next key aspect is area ratio. What area ratio is a comparison of the area of the aperture opening to the contact surface area of the aperture walls. This is important because if the ratio calculation results is in a value that is less than 0.6, your transfer efficiencies will start to reduce and your coefficient of variation will start to increase. If you have above a 0.6 for area ratio, you shouldn't have any trouble printing at all. You may want to consider adjustments when it's between 0.6 and 0.65, just to open up that process window if you can. Once you get below a 0.6 area ratio, but greater than 0.5, this is where printing with standard metal foils may not give you good results. This is where you may think about doing the upgrades we talked about, such as nano coatings or higher grain stencil materials. Anything less than an area ratio of 0.5, this is going to be a real challenge to get acceptable transfer efficiency and low coefficients of variations, regardless of the material, the design of the apertures. Aspect ratio is another ratio that needs to be considered in the design. This is a comparison of the width of the smallest dimension of the aperture to its thickness. And you want a 1.5 or greater is the target. But with miniaturization and all these advancements in stencil technology, I think area ratio is a better predictor of the performance, but aspect ratio is still something that you need to consider. The 5-ball rule. What this is it considers your paste ball size, which is defined by your paste type. So a type 3 has a little bit bigger ball size than a type 4 or a type 5. What the 5-ball rule is, if you had balls lined up in a row across your stencil aperture, 5 balls or more needs to fit across that aperture. And this is just a way to confirm that your paste type is compatible with these smaller and smaller apertures. If it's not, you may have to go to a higher paste type. Now, you can have the perfect stencil design, the perfect stencil construction, the perfect support, and you could still have print issues. Because the PCB quality that you get from your vendor is a significant contributor to bad gasketing. And some of the issues that a poor PCB design can create can be mitigated through stencil design adjustments. So for instance, fiducial accuracy and alignment. Panel fids are usually added to the rails of the board to square it up or put it into a panelized board. And sometimes those are off compared to the data. So by using board fids, you might find that you have a much more accurate alignment. So you want to make sure that you include both on the stencil, so you have options. Chemical overetch, that would require, I'm sorry, copper overetch. That would require additional reductions because this will cause defects from gasketing. And what that is the board house just, etched the copper a little bit too much, so the pads are undersized. So even though you did a 1 to 2 mil adjustment for gasketing, you could be overprinting if the pads are overetched too much. Using hassle finishes, and hassle is hot air solder leveling. This could cause an issue because you can get excessive buildup and doming on smaller solder pads. And this can create gasketing issues as well by holding up your stencil. PCBs can also have shrinkage, particularly in larger boards. What shrinkage causes is your pads and fids to be off as compared to the design. So a custom stencil can be created to accommodate significant shrinkage if it's consistent from board to board, but that really needs to be measured and mapped out properly to get the proper adjustments where it's needed. When you're working with panelized boards, meaning you have a bunch of small boards arranged in an array and attached together to create a larger board, making production easier and more efficient, there may be a tolerance stack up of the routings between the boards or the scorings, depending on if it's V-scored or routed. And this can slightly shift board images. And what you would need to do is you would need to map this and adjust the stencil images accordingly if it's repeatable. Now, sometimes the solder mask is shifted and can get on top of the PCB pads, and this can create significant gasketing issues. And it can be a significant PCB quality issue because it's not going to allow you to form the proper solder joints. So this may drive you to reject the boards altogether. And if the design contains mask-defined pads, there's really no real adjustments needed to the stencil unless the mask is so thick that it may cause excessive solder deposits, and you might have to adjust for that. So this is why it's imperative to have a good quality PCB supplier and not just the cheapest price one, usually coming from overseas places that shall not be named. Because cheap, poor quality PCBs can cripple your production and kill your quality, which will cost you more. Other common stencil design modifications that are needed to prevent certain kinds of defects or issues in production are sometimes needed based on your technology, and I've listed a few common ones here. So for instance, if you get mid-chip solder balls, these can be mitigated by using a home plate or an inverse U-shape aperture for your chips. And what this does is it reduces the amount of solder paste that is under the chip, and that paste may get squeezed out under the part during placement. And if it gets squeezed out and separated from the mass, it may not pull back and it will squirt out the side of your part, creating a mid-chip solder ball. So by using the U-shape, it removes that solder paste, reducing the squeeze out. QFN voiding in the thermal pads. This can be, the voiding can be reduced by reducing the amount of paste that you're putting down on the thermal pad, usually around 30% or so, and also window pane the thermal areas. This will help give the gases that are created by the flux or reflow avenues to escape. You can also extend the length of your apertures around the perimeter of the QFNs by about 10 mils if you have the room. And what this does is it actually raises the part a little bit during reflow because of surface tension and everything. And it just allows the gases that cause the voids a little extra room to escape. Now, BGA pads, those are usually round on the board, but making the aperture square with rounded corners will help improve the release and consistency, because paste releases better out of a square pad than a round one, or a square aperture than a round aperture. And you can also increase the aperture size on the corners, and that may help with stress relief in the BGA and the part. Bottom terminated diodes and LEDs, those may be prone to floating or voids. So you're going to want to look at doing reductions and maybe some window painting to mitigate the opportunity of voids, especially under high power LEDs, because they generate a lot of heat and they need that heat transfer away. And if you have voids, that could compromise that. Now, for larger pads or large lug leads or anchor pads where you need a more robust solder joint, overprinting will add solder. And you don't have to worry about printing on the mask, because the solder paste will pull back to the pad with surface tension during reflow. But the one thing you have to just watch out for is some solder masks have high surface energy, and that may impact the pullback of the solder. So you may get some minute solder balls where you overprinted. So if you mix size parts on your design, for instance, you have large parts mixed with smalls, or you have you want to implement intrusive reflow of plated through-hole parts, getting the right amount of solder volume to satisfy all these parts can be very difficult with a single thickness stencil. Because if you focus on getting all the smalls right, it's going to starve the bigs. Then you toss in the volume needed for plated through-hole joints, and you're just going to have a nightmare scenario. So some options to increase volume of solder paste in the stencil. Obviously, you can overprint on the mask, and this is really good for localized areas that need a little bit more solder while the rest is okay. The main benefit of this is that you can do this with a single thickness stencil. The challenge is that you need the space to be able to print that paste. And like I mentioned, some mask surface energy is such that the paste not pull back all the way, and you may get solder balls. You can also use the two stencil print method. This is where you need actually two stencils, one to print the smalls and a thicker one to print the higher volumes. You need to back etch the second stencil that prints the higher volumes with indentations so you don't smash the paste that you deposited during the first print. Of course, this is going to add additional stencil costs, but it will give you better control over your volumes. The big downside of this is you need two stencils, two printers if you're doing this in a full production line. So there is a really high investment to do that. You can also chemically etch a step called step stencils. This is where you start out with a thicker foil and then chemically etch down to a thinner stencil in the areas that you need less volume. The problem with chemical etch stencils is controlling that etch rate is super critical, and the step ups have a larger area of influence around them, which means that if parts are too close to that step, they're going to see more volume of paste deposit, which could cause defects. You can also create step stencils by micro machining or laser welding. So in the case of micro machining, a thicker foil is milled down to a thinner foil thickness before the apertures are cut. This is really good for stepping down smaller areas. It's much more precise, and it has a smaller area of influence around, so parts can be closer to the stepped area. Laser welding, that attaches a second piece of foil material to the base stencil, and it builds up that area needing more volume. So what you do is you laser weld around the perimeter to bond it to the thinner stencil, and then just cut the apertures through both foils. This is really good for building up smaller areas that you need more volume. And either one of these methods are very precise and controllable, and they have a very small area of influence, so parts can be closer without affecting their volume. Of course, there's a couple other methods to add paste outside of the stencil design. You can dispense or jet. That's an option to put down extra volume that you need, but it is going to require auxiliary equipment, another process step. This equipment can be mounted inside the printer on the camera head, or it could be applied after printing. But you got to make sure that the paste that you use for dispensing or jetting is compatible with the printer paste, with the fluxes, so they don't counteract each other. Solder preforms is also another option. This is good when you have the room to overprint, but just not enough to get the volume needed. They can come in different alloys, different shapes and sizes, and if they're packaged correctly, you can machine place them with your placement machine. All they need to be done is placed in a way that it's touching the solder paste, and all that solder will pull back and get absorbed into the solder reflow. Cost-wise, it can be pretty expensive if you go with the preforms, especially if you're putting down a lot of preforms. But it is a good option to quickly implement something, implement a solution with no added equipment, especially if you can, get it on your placement machine. And if you can get the customer to add it to their BOM and actually pay for it, that's a bonus as well, making it much more affordable. Pin and paste, or stencil printing for through-hole components. This is also called intrusive reflow, pin and paste, pin and hole. This basically, it all means the same. You're soldering plated through-hole parts in the SMT process. The whole purpose of doing this is to streamline the process, eliminate the need for downstream processes such as wave or selective solder or hand soldering. It's also a good option if you have only one or two through-hole parts, or the design of the board is such where it makes it incompatible with putting it across a wave or selective, and it's not very practical for hand soldering. But there's a lot of considerations. It's not an easy drop-in solution as some may think or hope. The first question is, can the parts even take the heat of the reflow oven? Or is there a high temp alternative? And there could be a cost associated with that. Can the part be packaged in a way to make it allowable for machine placement, or is it going to be hand placed in SMT? That can reduce your throughput rates. If it's machine placed, it's going to need a pick cap, or it has to have some kind of surface for the placement machine to pick from reliably. And you may need a custom nozzle as well. And you also need the room on the placement machines. Some of these through-hole parts are rather large. They can take up multiple slots on your placement table, and usually are placed in the last sections. So you may not even have the room on your placement machine to put a through-hole part for machine placement. So moving to pin and paste may add significant costs to the part, the process time in SMT, especially if you're hand placing. But if the costs and the impact is acceptable to you, then you have to now consider the amount of solder you need to create acceptable solder joints. So there's a series of calculations that need to be made to determine the volume of solder that you need. And I have the calculations here. So depending on the number of leads, if they're attached to internal ground planes, per IPC, vertical fill needs to be a minimum of 50% to 75% for class 2 product, and it has to be 75% minimum for class 3. Of course, we want 100%. We want nice fillets on the bottom and the top. This calculation considers all that, and it calculates the volume of the finished solder joint. Once we have the volume needed for an acceptable solder joint, keep in mind we have to double it to determine the paste volume needed, because the metal powder to flux ratio is about 50% in solder paste. So you're going to have to double it. Then you got to look at the aperture design. Can you design an aperture large enough and thick enough to get that volume that you need? Of course, your stencil houses, the designers there will help you with this calculation. You just need to give them some key information, such as your board thickness, your pin sizes, as compared to the holes, to help you determine the proper volume. Now, the layout of your PCB around those through-hole parts that you want to pin and paste, that may restrict over printing. So, going to the step stencil, using preforms, or dispensing additional paste, those are all options that you would need to consider to get the volume you need. Now, you need all the paste volume that you can get to create that solder joint, but inserting the through-hole part can actually reduce the volume, because it can push the paste out to the end of the pin when it's inserted through the paste. So as you go through reflow, it could drop off at the beginning of your reflow zones around zone 1 or 2 from hot slump. They start looking like little mouth droppings in your oven. So splitting the apertures can help provide clearance for the pins and reduce that paste loss. Just make sure if you make any modifications to make clearances, that the overall volume is maintained. Okay, so that covers stencils. Do we have any additional questions before we move on?
Yep. Ray, we just need to time check. We're at 3:11 right now, and we do have 2 additional comments in here. Besides the recommendations for good solder transfer, is there any additional difference/recommendation for different solder medium? Example, air, nitrogen, or vapor phase? Question mark.
Well, well, we're talking, just on the printing side. You can reduce, change your paste type. Let's say, you could go to a finer paste, like type 5, type 6, whatnot. But you got to be very careful, because that could cause other process issues in reflow, such as graping, or, it could start creating solderability issues because of oxidation. So then you may need to consider nitrogen or stuff like that. Now, we are going to be doing a webinar on the reflow process here later this year, so we can cover that during that as well. But can you also repeat the question, Mike, just to make sure I...
So there were 2 parts to this statement here. Is there any additional difference/recommendation for different solder medium, air, nitrogen, or vapor phase? Part 2 of the question is, we are using vapor phase, and in comparison with reflow in air, we see better results with larger aperture reductions, sometimes up to 60%.
Okay. I don't have a lot of experience with vapor phase reflow, but it is a very stable process, a very controllable process. And the fact that the vapor is, prevents any air while you're doing the reflow process. So I can see that, having much better wetting, much better appearance and results.
Okay. And one last question here from the same Zalard Balarka here. Is there any rule of thumb to figure out when overprinting is not a solution anymore and you need to move to step, stencil, or preforms?
It's really going to come down to space. The paste can be printed pretty far out, pretty large overprint and pull back. So overprinting is not a big concern unless you have mask with high surface energy creating solder balls. But it really comes down to the space. Can you get the volume needed in the space that you have with the surrounding parts? That's really what it comes down to.
Okay, one question just came in this minute. From Norm, thank you, Norm. Will multiple printing stroke also help increase solder volume in pin and paste?
Yes, if you do a double stroke print, it's going to pack more paste into the holes. The problem with double printing is, you're increasing your cycle time for one, but also you could start compromising the other parts on the board, causing squeeze out underneath the stencil because of the fill pressures, and so you can start seeing solder bridges or other issues with the SMT parts. So you got to be a little careful with double stroke printing. But yes, it will add volume to the plated through holes because it's going to pack more solder in there.
Okay, that's what we have for questions now. We have one more. Ryan Maturi, I heard the figure 1 to 2 mil reductions stated. Is it better to use a percentage such as 10% instead, specifically for discrete components?
To be honest with you, I used the percentage when I designed my stencils, and it was kind of a blanket percentage. A lot of, you got to watch with that, because is that percentage, especially when you're dealing with bigger apertures, is it going to increase that reduction and causing you to starve the joint? So you got to be careful with that. The whole idea of that 1 to 2 mil reductions is just to get the window of the aperture 100% on the pad when everything's lined up.
Okay. All right. Time check is 3:16 right now. We are running over, so let's keep that all in mind. And thank you, everyone, for your patience. We'll continue.
Got just a few more slides. We're going to talk about squeegee blades. I'll zip through these to get everybody back to their day. So with blades, we're going to cover different types, different style of print angles, and how those styles and print angles affect your printing, as well as we're going to look at when do you know it's time to replace your blades. So the function of the squeegee blade is really to spread that solder paste over the stencil and fill the apertures. So as the print head moves across the stencil at a certain set print speed, it exerts pressure through the set print force in your program. That print force needs to be strong enough to overcome the pushback force of the stencil. If not, that blade will start to float, and it's going to leave a haze of paste behind your squeegees. And this will cause you not to have a clean swipe, and it may cause deposits to be inconsistent. The squeegee print angle and the print speed, this is what facilitates the paste rolling action. This rolling action creates the shear thinning that you need for the paste to lower its viscosity, and it also helps you fill the apertures. Now keep in mind, print speed and print force are interrelated. The faster you print, the more pushback you're going to get from the solder paste, the higher the print force you're going to need to get a clean sweep. But you only want to apply enough print force to get that clean print with no haze left on the stencil. Because if you apply too much print force, it can damage the stencil. It can wear out the blade through excessive wear, and it also could cause bleed out of the apertures past paste past the apertures. Print force also has the effect on the blade, changing the angle of contact, which is called the attack angle. So if you're printing with a squeegee that's at 45 to 50 degrees and you exert pressure, that attack angle may actually be closer to 40 or less due to squeegee deflection. And at these lower angles, more pressure is going to be exerted on the paste in a downward, and it has an effect on increasing that fill pressure. And if the fill pressure is too much, it could force paste to get under the stencil, causing those bridges for ultrafine pitch, solder balls, increased stencil cleaning, things of that nature. So you can increase the print angle, and that will reduce the attack angle effect. But when you increase the print angle, say to 60 or so, it may cause scavenging on large open apertures, and then you'll get insufficiency on those. Reducing the print force will also reduce the attack angle, but again, if you back off too much, it's going to cause the haze and create printing issues. Now, some blade manufacturers, they compensate for the attack angle deflection by using thicker or harder materials, or they apply hardness coatings to the blades, or they engineer the blade edge profiles to reduce the deflection. And what that does is it can improve performance, especially when you're doing higher speeds and pressures. But again, those things are also going to come at a higher cost. Also, how much blade projects past the holder itself, that will also impact the amount of deflection and the attack angle. So when blades wear, what happens to them? Well, for some people, they fall into what we call a vicious cycle. Now, this slide is courtesy of Chris Shea from Shea Engineering Services, and it's a perfect illustration of this. And what it is, you know, you have a new blades and they perform well at a given pressure. They have a nice clean sweep, no haze. But as it wears, you start seeing residual solder haze start to appear after the print on the stencil. So what do? Well, we just increase the pressure a little bit and move on. Well, the blade continues to wear. You start seeing that residual solder film again. You add the pressure over and over again. Now, what happens is the stencil starts to wear out too. Then your print quality drops. You may try further adjustments to the force and speed and all these different things, but the blades and now the stencil are too far gone, and it can create defects. And that is what we call the vicious cycle. So please avoid that at all costs. So then you might ask yourself, so why not change blades on a scheduled PM? Maybe opt to do it weekly or monthly or quarterly or whatever. In theory, that's great, but wear is caused by use. And unless we have a very steady print rate day in and day out, total control of our process, and keep things at fixed pressures and speeds at all time, optimum support setups, we only use one set of blades on the same printer all the time, and have good traceability, then we could probably accurately determine when it's time to change your blades based on performance and predict that for the future. But not everybody has that ability. So, and this also could cause an increase in blade consumption, and that is going to add more cost to consumables, especially the higher end blades. So instead, it may be a better method to just implement checks to inspect the blades before use and after cleaning. Run your finger down the edge and check for burrs or dings. Just look at the blade. Does the blade look warped or rippled in the holder? If the answer is no, then consider blades good for use, but the final determination is going to be in the results of the print. Look at the stencil as it prints for the signs of haze, or if you start seeing paste lines left across your artwork. These are both indicators that your blades are worn out or damaged and they need to be changed. Now, also, squeegee blades can be easily damaged through handling. They can get dropped, they can get banged together in the cleaner if they're not secured properly, or through poor storage practices. Save the blades, control the handling, limit the opportunity for damage. And it's recommended that the blades are kept together in a set and always used together. This helps ensure that the wear from usage is the same throughout their life. So that being said, when one blade gets damaged and needs replaced, you really should replace both to maintain that similar wear patterns. Just keep in mind, solder blades are consumables, So don't be afraid to change them as you need it because of cost. You're going to save the money on quality and downtime improvements over the cost of the blades over time. So in summary, if you invest in proper support setups, use the right stencil materials and design standards, and monitor and care for your squeegee blades, you'll establish an excellent foundation for a stable process, and you will see improved quality. So thank you very much. My apologies for running over. We had a lot of material to cover, and we know your time is of value, but I hope you found this beneficial. And we're going to send out a short 5-question survey out in email. Please make sure it doesn't go to your junk folder. And, you know, I know filling out surveys suck. That's why we kept it to the 5 questions. But we appreciate it because it helps us get better. And as a thank you, everybody that returns a completed survey, they'll be entered in a drawing for an Amazon gift card. And that's just our way of saying thanks. So this concludes the second webinar. Our contact information is shown here on the screen. Please feel free to reach out to us to answer any questions or to explore how we can help you succeed. Just remember, we offer independent machine capability analysis services, measurement equipment. We have on-site IPC certification, operator and process training, and process auditing consulting services, because we're here to help you optimize your people, process, and equipment. So are there any final questions to wrap this up?
I don't have anybody in the chat, just a few people saying thanks for the good presentation. And again, let us know if you have anything. If not now, please provide it in the survey if you can. That would be great. All right.
Okay. Well, thank you very much, everybody. I appreciate your time.
Thanks.